Okay, this is ESILsolve, a symbolic execution engine using ESIL. My name is Austin Emmett. My handle is Alkali. And a little bit more information about who I am. I'm a mobile security researcher at NowSecure, where I work on automating security tests for mobile applications, so apps on iOS and Android. I work with Pancake, Edu, Grant, many others. In university, I studied math and physics, but I sold out and did information security instead. I think it's been a good choice. I have a lot of fun. Got a background in doing CTFs and game hacking. That's what I did when I was younger. It got me into security. And I've worked as both a reverse engineer and a boring software developer in my previous roles. And recently I've gotten into emulation and symbolic execution, and that's why I started writing this tool. And my Twitter handle is AlkalineSec. Alright, so we're going to dive into a quick example to kind of get us psyched for symbolic execution and ESILsolve. So right now this is the main function of a binary from the Google 2016 CTF. So what it does is just copies in arg1 into this buffer, and then does a bunch of validation using all these function calls on the right here. So we're going to take a more in-depth look at what's actually going on here in R2. Okay. So it's called Unbreakable is the challenge name. I'm going to navigate to main and see that. So what's going on is it's just checking to make sure there are two arguments, and then it copies the arg1 into the buffer at 6042CO. And then it calls all these validation functions we'll see here. So we'll go to OE. So here we see that it's copying in 1 byte at a time into the registers, and then doing some XORs, some subs, some adds, and some compares based on those byte values to do the validation. And in the false path, it's going to return, and the true path is going to call out to this function. And this function is the product activation failure function. So basically, if that jump not equals takes the true path, it's going to go to fail. So we want to avoid that path, obviously. So each of these functions is going to have that same kind of structure: copy in some bytes, do some XORs, do some subs or adds. This one just adds XORs, and then do the comparison. And if it's good, it returns to the main to go on to the next one. So down at the very end, there's a call to this final function, and this is just the product activation. So this is how you know you succeeded. Your value is good if it passed all those tests and got to this function. You know that you have put in the right string. So this is a good candidate to use with ESILsolve. So we're going to run Python unbreakable.py, which uses ESILsolve to solve this challenge. In a couple seconds, it will produce the string, the flag, and there it is. So really simple solution. We're going to explain what goes on in here as we go through the talk. But as you can see, this is just very simple to solve these sorts of challenges with ESILsolve and really any other symbolic execution tool. But this one is great because it uses R2. All right, so going back to the slides. All right, so symbolic execution, a very short review. Symbolic execution is the emulation of a program with the ability to make some data, memory, or register values symbolic. Using symbolic values allows exploration of code paths without needing to know the concrete values that actually reach them. Those concrete values can actually be solved for later. So taking conditional branches splits the state, the program state, which is just what's in memory or in the registers, and PC is constrained to one value, one of the jump targets in each of those new states. So you're making copies of the state, one for every possible target of a conditional jump, and then you are constraining the PC register value to be the corresponding value in each of those new states. So think of the difference between emulation and symbolic execution like the difference between arithmetic and algebra. So in arithmetic, we have just simple expressions like 4 plus 4, and it has a concrete value 8. Whereas in algebra, we can have symbolic expressions like 4 plus x, where x can be any number or any number within some range. You can have constraints, just like you can have in symbolic execution. So to extend this metaphor a little more, in algebra you can solve for equations like 4x plus x equals 20. You can solve for the variable x. So that same kind of expression is generated when you symbolically execute this code here on the left, with the input int sent to a symbolic value and the false path is taken. So here we have just a scanf, which takes an integer and then a series of instructions. So we have the value x is stored in EAX and EDX, and instruction shift left EAX2 is equivalent to 4 times x, and add EAX EDX is another addition of the x value, and so you get 4x plus x. And then finally, the comparison of EAX to OX14 is the same as the equals 20 part of the expression. So then when you constrain that jump to take the OX758 path, you are basically constraining that expression, 4x plus x equals 20. You're constraining that expression is true. So constraining this PC value constrains the other symbolic values involved in the jump condition. And in SMT solver, we use Z3. It's a very common, widely used SMT solver. It is used to evaluate the expression and get concrete values. So there we constrained that EAX was 20. And so in constraining that expression was basically 5x equals 20. So in constraining 5x is 20, we're basically also adding the constraint that x is equal to 4. So that's the basic idea of symbolic execution. For more in-depth analysis, for more in-depth explanations, I definitely recommend reading some more about other tools. And so some other tools you might have heard of are Anger, Manticore, Clee, Mayhem, more recently SimCC and Sys. And so it's a difficult kind of concept to explain. And so one of the best things to learn how to do it is definitely just to kind of play around with these tools, read about how they work, and just try it out. All right, so we can see here some debugging output of ESILsolve on the right. So these are the ESIL expressions, which we'll get to next, and the instructions that are being executed, and the symbolic PC address that eventually builds up based on the execution of these instructions. And so this is after we have made the initial RDI value a symbolic bit vector expression. So you can see in that value there, the symbolic PC, we have that inner extract 31 0 RDI, and that is basically just taking the first 32 bits of RDI, which is EDI, and is comparing it to 2. And that makes sense because in the left-hand code there, we can see that the comparison is taking, well, first what was done was EDI was moved into that var4h location, and then that var4h location is being compared to 2. And that jump not equals there afterwards. So that is how we get this symbolic PC address. And then we can see that if that extract EDI out of RDI is equals 2 is true, then we're going to get 0, and that's compared to 0. So basically, that is encoding the jump not equals there. And then the two values of that outer if instruction are 1547 and 1554, which you can see below are the two possible values of PC after this jump, OX60B and OX612. So that's basically the simplest possible example of a conditional jump and the symbolic value that PC then has. So here's a less simple version of the same thing. We have a lot more operations that are used on similarly another symbolic RDI, and what's going on here kind of it's difficult to see in the resulting expression here on the right. This is after it's been simplified, and Z3 kind of simplifies things in a bit-by-bit way. But on the left, you can see that it's, you're doing a XOR, you're moving some constants, and you're doing some multiplications, some XORs, some shift rights, and then you're doing a comparison of the resulting value with, which ends up in EAX, and you're doing a comparison to OX11E7. So this is the symbolic PC that you get out of that. And as you see, it's much more complicated. So in real programs, we're going to get some very complicated expressions out of this symbolic execution. So moving on to just the actual IR that ESILsolve uses, it's ESIL. It's DAY2's built-in intermediate language. It uses a simple stack-based system to express any instruction as a string of values and operators. So add x0, x1, x2, that's an AR64 instruction, becomes x2, x1, plus, x0, equals. So what's happening there is x2 is being pushed to the stack, x1 is being pushed to the stack, the plus operator is popping those two values off the stack, and then pushing the value x1 plus x2 to the stack. And then x0 is pushed to the stack, and then the equals operator pops x0 off and then assigns it the value x1 plus x2. So it's actually very simple, it's very readable, and it's really great for understanding what an instruction is doing if you don't know that instruction, and it's relatively simple. But it actually turns out that it's also an interesting and pretty good IR for symbolic execution. So this has been like a very short talk on ESIL. If you want to know a little bit more about how it actually works, there's a great talk from last year's R2Con, and so I recommend you check that out. It's very good. Goes into a good amount of depth about what's actually happening when you're executing an ESIL instruction. Right? So challenges of ESIL-based symbolic execution. So the most obvious here is that ESIL is a lot less verbose and precise than other intermediate representations. So on the right here, we actually see the vex representation of add x0, x1, x2. So vex is another IR, and it's one that Anger uses to do it's lifting, and it's the actual expressions that Anger symbolically executes through the vex engine. So you can see here, every value and operation has an explicit size and type and signness, and so this is very much true of many other intermediate representations. They're very strict with those qualities of each value. And so it turns out they're being actually overly cautious dorks. You don't really need all of this information explicit in every expression. And the implicit way that things are handled by ESIL is perfectly well formed enough to make a symbolic execution engine, which really means that it's perfectly well formed enough to encapsulate everything you need to know about what's happening in the instructions. Save for a little bit of additional metadata about the length of instructions. But whenever you do your lifting, you're going to know that information anyway. So the real challenges of ESIL is based on the symbolic values on the stack. So as we saw before in vex, they're using this temporary variable method where each of the intermediate values when an instruction is lifted and then emulated is stored in these temporary registers or temporary variables called T0, T1, T2. And so in ESIL, instead of doing that, we push values to the stack. And so it turns out you kind of need to have this symbolic stack, which is a little bit more complicated than just having separate symbolic values in each of the temporary registers like vex does. So we're going to show a little bit of the code that's necessary to actually run this, to do this. So this is the ESIL process class, and it has a couple of methods that are the core methods that actually execute instructions. We can see execute instruction here. and then the parse expression, which does the actual parsing of the ESIL string. So you do the split, and then we're looking at each individual value or operator. And the most important part is going to be handling these conditional operators. So we see that we're, have these special handlers for if the if, then, and else words. So we also have an exec type, so that basically allows us to treat conditionals that are symbolic and conditionals that are concrete differently. So we have the exec and no exec state for ones where we know for sure whether we're just executing the if part of the expression or we're executing both the if and else, which is what we need to do when we have a symbolic conditional. So in that case, when we have a symbolic conditional, we need to execute both parts of the ESIL expression, both the code contained in the if part of the brackets and the else part of the brackets, and then we need to unwind the stack afterwards and then have a new set of symbolic values pushed to the stack that are of the form if condition. We have the if value that was on the stack, and then otherwise we have the else value that was on the stack. So then there's also the difficulty of the go-to operator, which uses basically arbitrarily nested conditionals. Is a different way you can kind of think about it. If you thought of kind of telescoping each of the go-tos, replacing it with kind of the ESIL expression again and again, you can see this basically the same as arbitrary nested conditionals, and that creates a host of issues. So if it basically, what we eventually do is having a hard cutoff of how many times we can symbolically deal with a symbolic conditional that leads to a go-to. If it's a concrete value, we can just run it normally, but if the condition involving the go-to operator is symbolic, then we need to have some cutoff because the size of the expressions will grow very large very quickly. But it turns out the other operations involved in ESILsolve end up being pretty efficient ones for Python, which is good, obviously. But you can check out the rest of the source code. It's pretty simple. It's only 1,600 lines of code or so in total. So, moving on. Okay, so these next couple slides are about the ESILsolve API, but we don't have enough time to actually go through each of these things. We're going to actually just go through them in the context of going through a couple demos of different examples of solving of challenges with ESILsolve. So just here is the ESIL solver. This is the main class. You see on the right just an example where you can see some of these methods used. Then we got the ESIL state, which is the other thing that you'll mostly be dealing with when you write a tool using ESILsolve. So that just has the program state, the memories, the register, the memory, the registers, the ability to constrain bytes and evaluate different bit vectors and that sort of thing. You can also make copies and then step the instruction, just like in a debugger. All right, so we're just going to move on to demoing so we can go faster through this. All right, so we had our first demo, which was Google 2016 CTF, but we got some others here. So the first anger example that they give is this R100. So we can see, here that it's just this very simple binary. Here we go. We just do some simple things here. We could call this function OD, and it just does this not very complicated validation function here. So we can symbolically execute this code and see what we get using ESILsolve. Here is our solution. Very simple. We're just using a solver with the R100 binary. We're going to a call state that is the beginning of that validation function. We're going to define an address, and then we're going to set RDI to be equal to that address, and then we're going to write in this flag value into that address using state.memory. So that flag value is just going to be a Z3 bit vector called flag. We're going to make it 12 bytes long, and then we're going to do state equals ESILsolve.run. So that's just symbolically executing the program with ESILsolve until we reach that target address. You can also put in a R2 symbol name there, so like sim.check or whatever the function you're trying to get to. You can also pass avoid addresses. So avoid addresses will make the execution quicker by just if you reach some address there, it will just stop executing those states anymore. So it'll just kind of constrain, not constrain, but it'll just narrow down the number of states that you're currently executing. So the more things you avoid there, the quicker it will be to reach your target, generally. And so then once it reaches that final state, it evaluates the string, that the bit vector flag. It evaluates those bytes as a string, and then it prints it out. So we can see here, we do R100. It should be pretty quick, and we get the solution, code talkers. So that is the concrete value that passes through that validation function that we just looked at. Another good one to try out is this AIS3. Oh, I can't type. So this one is a good example of registering a hook. So here we do similar things to what we did in the R100, but here we have a call state to sim.verify, showing you can use the flag names. Then we have RDIs also going to be equal to an address where we write a symbolic bit vector. And then we register a hook. And then here we don't set a target or a void address, just because basically this check function is going to be functioning as both those things. If we reach the address there, the 5BD address, we do this check, and we constrain ZF to be 1, and then if that is satisfiable, then we just evaluate the flag and print it out. So you can see this one also runs very quickly. Should run here after a couple seconds. Yep. This is just another example of a very quick CTF challenge that we can do very quickly with ESILsolve. Okay, so before I edit things, or before I move on, I want to real quick go to one of the most interesting and useful aspects of ESILsolve, which is that in the ESILsolve plugin we can use ESIL expressions that we write to constrain the state and actually use this to prove that different sets of instructions are equivalent to simpler operations. So we're going to pop over here, and we'll show this in the next slide here real quick, but it's the example on the right here is going to be what we're demonstrating. So we're going to go here. I'm going to clear this out. So we have this binary rotate, which implements left and right rotates, but in a not very simple way. So you might see something similar to this when you are dealing with some sort of obfuscated binary where they have, they've obfuscated the instructions that are doing something simple and made it very complicated. So here you can see that in the shift left, this rotate left method, we have a bunch of shift rights and we have a bunch of subs and adds and things. And this is actually implementing the rotate left, but it's very difficult to see that. And so if this function were not called the rotate left, you might not know for sure that that's what it did, and you might kind of develop an intuition that that's what's going on here, but you want to know for sure. And one way you can do that is you can use the ESILsolve plugin. You can initialize it using the ASXI. You can initialize the RDI value to have a number value that's symbolic. That's what's going on there. We're going to set RSI, which is the number of bits to shift, or the number of bits to rotate by. We're going to set that just to the concrete value of 12. We can also do this in a symbolic way, and then we could set hooks in like a full Python script using ESILsolve that show that for every RSI we're going to get the equivalence of the left rotate. But here we'll just show that if RSI is 12, we're going to get a left shift of 12. And so then we can just run until we get to the end of this function. And then we can do a push a context in the constraints. So this allows us to just push constraints that then we can later pop off just to check to see if whether those constraints are satisfiable without having to permanently alter the constraints of the state. And so then we're going to go XC, which allows us to execute an ESIL expression and evaluate or constrain the results. So the C makes us constrain the results. We're going to do ESI, EDI, and we're going to do the left rotate operation. And then we're going to do EAX, which is the return value. So this return value we think is the left rotate, but we want to prove it. And so this is how we're going to do that. And then we're going to do a not and say that it's not 0. So basically what we're saying here is we're constraining the return value to not be equal to the left rotate. And so if we are right, then this will not be satisfiable. We will get an error here when we try to evaluate RAX, and that is what we get. And then we can see that if we pop off our constraint that we put on there, that we will be able to evaluate RAX, and we can see that that means that that constraint that we just put on is not satisfiable, which means that EAX is in fact equivalent to the symbolic left rotate of EDI. So any value that you put in EDI, the return value is going to be equal to the left rotate that we put in. So that's just a really cool way of showing, with this plugin that some sort of obfuscated operation is equivalent to something much simpler. And so this is kind of a toy example, but you will see in obfuscated binaries things like this. And it's just really cool to be able to simply write an ESIL expression that is basically being used as a SMT proof of two things equivalent. So this is something that people do kind of an ad hoc way using, I've seen people just take decompiler output and then they kind of shift it around so it fits into the syntax of an SMT solver, and then that's how they prove that certain obfuscated expressions are equivalent. But this is just a really easy way to do it automatically using symbolic execution and being able to write ESIL expressions. So this is the power of having a readable and writable IR that we are using to actually do the execution. I thought that's cool. So next thing I want to cover is just really go through quick. Using ESILsolve to improve ESIL. So symbolic execution of ESIL allows us to convert the string expression of the AST into an AST, which we can compare to the ASTs generated by other symbolic execution tools. So we can symbolically execute something with ESILsolve and then with anger, and then we can take the two expressions and then say, assert that they're not equal, check to see if that's satisfiable, and if it is satisfiable, then we know that there's some difference in the implementation of our execution. And so that's really a powerful way to test whether the ESIL expressions are right, or at least right compared to, at least in agreement with other tools. So that is what this tool called ESILcheck does. So future goals, I'd like to use ESILsolve to prove the equality of ESIL expressions and other IR expressions, what I was just talking about, and fix them if necessary, or cover more architectures more faithfully. So like we definitely need to do some work in MIPS and maybe some like PowerPC stuff if anybody cares about that. I also want to make a modest procedure library so that we can cover some common libc functions, so that running them manually, running the actual assembly causes state explosion. So we want to avoid that. So we want to do the same thing with syscalls, and I want to eventually maybe create some sort of fuzzer that leverages ESILsolve and concrete SL emulation and maybe R2 Frida, and I think that'd be really cool to generate really great coverage guide fuzzing that uses symbolic execution to get the very difficult code paths, and also uses Frida for doing some in-memory fuzzing, basically to verify that crashes are real. So thanks to Pancake and everyone that's worked on ESIL and DAY2. It's a great community, and thank you for coming to my talk or listening to my talk.